And we're back. Today we are going to talk about the mole, which is what we use to count atoms, which is a more efficient way of doing it instead of grams, since atoms are so small. So a mole, one mole, or sometimes you will see it abbreviated instead of MOLE, just MOL. And while I know that's not a very efficient abbreviation, it's only eliminating one letter, that is the standard way in which the mole is abbreviated. So the mole is what we use to count atoms in chemistry, and it's also the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. So remember, carbon-12 is what we use to define the atomic mass unit. And remember, carbon-12 weighed exactly 12 atomic mass units, and then the mass of every other atom after that is based on that. So the person who came up with this was Avogadro's number, and he came up with the conversion factor that 1 mole of anything is equal to 6.022 times 10 to the 23rd units of that thing. So this is his name, Amedeo Avogadro, not avocado. And he came up with this number, and sometimes you'll see it as 6.022, or normally we'll use just 6.02 times 10 to the 23rd. So he's able to use the number of moles to be able to convert to number of atoms, and that's where we get all of our atomic masses from on the periodic table. They are also referred to as molar masses. So for example, carbon, its atomic mass is 12.01 AMU, or we would refer to it as the molar mass of carbon, 12.01 grams over moles as the molar mass of carbon. So we are going to use all of these conversion factors to convert between mass and moles and mass, and moles and atoms to moles. So first off, I'm going to show you how to convert between the number of moles of a given atom or molecule to atoms of a given molecule or atom. So let's say we want to calculate the number of iron atoms in a 4.48 mole sample of iron. So always, when solving these sorts of problems, you have to think about what you're given and where you have to go, and how do we get there. So always with these types of problems, automatically first thing you should do is write down what's given to you in addition to the units. So here, we are given 4.48 moles of iron. And for this, not only should you write the unit, so the unit here is moles, but also whatever element or compound it is. So not just 4.48 moles, but 4.48 moles of iron, Fe. So this is where we're starting. Moles, and we have to think about where we're ending up, and the question is asking us to calculate the number of iron atoms. So that means this type of problem, we're converting from moles to atoms. So we use our conversion factor. We know for every 1 mole of anything, and specifically 1 mole of iron, is equivalent to Avogadro's number of atoms. So for every 1 mole of Fe, there's Avogadro's number of atoms of Fe. And you know it has to be set up this way since we have to calculate the units of moles. And since Avogadro is an exact number, you're just looking at the sig figs that we start with. So we start with 3 sig figs. So our answer is also 3 sig figs. And when doing these problems, make sure you also do them in your calculator. You are careful with writing out the scientific notation, where you use the EE button on your calculator. So you should get an answer of 2.70 times 10 to the 24th atoms of iron, atoms of Fe. So in general, time you were asked to convert between moles and atoms, it should always look the same way. So you'll always start with moles of what's given. Then you'll always multiply by Avogadro's number. Over 1 mole of that given atom. So that makes sense. Those cancel. You're left with atoms of whatever you are being asked for, the atoms of the given element. And one thing I want to point out for doing these conversions, atoms refer to elements, but this conversion also applies to molecules. Which sometimes you'll just see abbreviated MOLEC. So molecules reference covalent compounds. And sometimes you'll see formula units. And formula units refer to ionic compounds. So anytime you're asked to use one of these, each of these are called representative particles. So anytime you see one of these, you'll have to use the same sort of conversion. You'll have to use Avogadro's number to convert to one of these. So you should be able to convert from moles to atoms, and vice versa. You should be able to convert from atoms to moles. And if you are asked to convert from atoms to moles, it's just the reverse. You're given atoms of something, and so now instead of multiplying by Avogadro's number, now you are dividing by it, and that's per 1 mole of that given atom. So the atoms cancel, and you end up with your units of moles of that given atom. Okay, so you should be able to convert between moles and atoms, and vice versa. Okay, now you should be able to convert between moles and mass using molar mass, which is the mass in grams of 1 mole of that substance. So for any element, the molar mass is easy. It's just the mass that's directly on the periodic table. So for nitrogen, you look on your periodic table, its average atomic mass, or now what we're calling molar mass, is 14.01. So that's the number of grams that's in 1 mole of nitrogen atoms. Okay, so that's just for elements. That's easy. That's directly what's on the periodic table. However, we can do the same thing for compounds, but we just have to add those individual molar masses together. Okay, so H2O, that means there's 2 hydrogen atoms, so we have to multiply 2 by the mass of hydrogen. And the mass of hydrogen on your periodic table is 1.01 grams per mole for hydrogen, and then we have to add that to the molar mass of oxygen. And there's just 1 oxygen, so we don't need to multiply it by a number. So we take 2 times 1.01, 2.02, plus 16, and we get a molar mass of H2O of this compound of 18.02 grams over moles. Now, if we want the molar mass of BaNO3 2, it's a little more complicated due to these parentheses. So remember, this 2 in O3 applies only to what's in parentheses. So we still only have one barium atom, which has a molar mass of 137.33. And we add that to now, this 2 applies to everything that's in parentheses. So we have 2 nitrogen atoms, so 2 times 14.01. And now we have to add, so 2 times 3, there are 6 oxygen atoms in BaNO3, so 6 times the mass of oxygen, so 6 times 16. And when you add those up together, you get a molar mass of this compound of 261.35 grams per mole. Okay, so you should be able to calculate the molar mass of any compound. And sometimes you'll see it as molar mass, sometimes you'll see it as molecular weight. That is the mass in grams of 1 mole of compound. And you should be able to, and much like how you should be able to convert from moles to atoms and atoms to moles, you should also be able to convert between moles and grams. So let's say here I wanted to convert from moles to grams. In general, you take the moles given, and if I want to convert to grams at the end, the grams of what's given to me. So if I want to convert to this mass, I have to multiply by the molar mass. So the molar mass goes here, because it's grams per 1 mole of what's given to us. So moles to grams, you're multiplying by molar mass. Grams to moles. So if we have grams of something that's given to us, and we want to convert to moles of what's given to us, in order to cancel out these units of grams, grams has to go on the bottom here. So the molar mass of that particular element or compound per 1 mole. And remember, molar mass is always the mass of that substance, whether it's an element or compound, per 1 mole. So if I have 0.494 moles of beryllium, and I asked you how many grams are in this number of moles of beryllium, so this is a moles to grams problem. I'm asking for grams, and not just grams, but grams of beryllium. So you know, moles to grams, you have to multiply the molar mass by the molar mass of beryllium, which is 9.01. So 9.01 grams of beryllium over 1 mole of beryllium. So those units cancel. And when you multiply it out, we ignore the sig figs of the atomic mass. Here there are 3 sig figs. So in our answer, there should be 3 sig figs. So here you would get an answer of 4.45 grams of beryllium. Right, so that's from moles to grams. If it's the opposite, if you're trying to convert from grams to moles, so let's say I give you, or you have 7.81 grams of zinc, and I ask for the moles of zinc. Now, since you have grams, the molar mass goes in the denominator. So the molar mass of zinc is 65.39 grams of zinc for every 1 mole. So now, when you divide that out, still we start with 3 sig figs. You end up with a value of 0.119 moles of zinc. So grams moles to moles, you divide by molar mass. Okay, so individually we've converted from moles to atoms, atoms to moles, and moles to grams, and grams to moles. So now, each of those was 1 step. Now we should be able to combine those. So here, I'm asking for the mass. So this is atoms to grams. So this is going to be a two-step problem. Since it's exactly one atom, we can ignore that sig fig. So we start with one atom of copper, and we know eventually we want to get to the mass of copper, or grams of copper. So first off, we know we can't directly convert from atoms to grams, so first we have to convert to moles. Okay? And atoms to moles, we have to divide by Avogadro's number. So there's 6.02 times 10 to the 23rd atoms of copper for every 1 mole of copper. So that's our first step, atoms to moles. Second step, now we have to convert from moles to grams by multiplying by the molar mass of copper, which is 63.55. So units of moles cancel, so we're left with units of grams. Remember, we divide by everything that's in the denominator in the bottom, multiply by everything that's in the top in the numerator, and when you do that, you get an answer of 1.056 times 10 to the negative 22nd grams of copper. And when doing all these problems, you should think about if your answer makes sense. So if you think about 1 atom of copper, that's definitely not going to be like 5 grams or 10 grams or a kilogram. It's going to be some mass that's incredibly, incredibly small, since you know the atom, any atom, not just a carbon atom, is incredibly small. So same thing, the reverse of that, if you have some gram sample of copper, so 63.55 gram sample of copper, that's going to be many atoms, since the mass of an individual atom is so small. So now this is the reverse. Now converting from grams, and I'm asking for the number of carbon atoms. So this is a grams to atoms problem. So still two-step, but it's just the reverse. So we start with gram copper. In order to convert to moles, we have to divide by the molar mass. This is convenient, since we started with a mass that's equivalent to the molar mass of carbon. So after this first step, 63.55 divided by itself will just be 1. And then second step, now to convert from moles to atoms, we just multiply by Avogadro's number. And when you do that, 1 times Avogadro's number, your final answer up here will be that same thing, 6.02 times 10 to the 23rd. And still always with your answer, make sure you put units, so atoms. And atoms of what? In this case, it's atoms of copper, Cu. So you should also be able to make comparisons between different masses of different atoms. So let's say we have 100 gram samples of magnesium, zinc, and silver. And you have to figure out which one contains the greatest number of atoms. So we have to think about how we are going to set up this problem. So we know already what we just did, mass to, or grams to atoms. So we start out with 100 grams of each one. And we know, in order first to convert moles to moles, we are going to have to divide by the molar mass. Because the grams per mole here, the grams will cancel. And then the setup will be the same for all of them to convert to number of atoms. So it'll be the same. We'll then have to multiply by Avogadro's number, because there's Avogadro's number of atoms in every 1 mole. So now we have to look at the difference between magnesium, zinc, and silver. So the molar mass that goes down here, the one that will produce the greatest number of atoms, that will produce the largest value here, will be one that has the lowest molar mass. So if we look at these 3 molar masses on the periodic table, magnesium has a molar mass of 24.31 grams per mole, zinc has a molar mass of 65.39 grams per mole, and silver has a molar mass of 107.87 grams per mole. So that means magnesium will produce the greatest number of atoms since it has the lowest molar mass. On the flip side of that, since silver has the largest molar mass, it'll produce the lowest number of atoms. Okay, not only should you be able to convert between grams and atoms and grams and molecules, you should be able to, when you have a compound, be able to convert to individual atoms in that particular molecule. So we are just going to do this one for water. Convert 100 gram. So we're going to convert 100 grams of water and see how many oxygen atoms are in 100 grams of water. Okay, so that means we're converting from grams to oxygen atoms. Okay, so we are going to start with 100 grams of water. And first thing we need to do, we know we can't convert directly from grams to oxygen atoms. We first have to convert to moles, and to do that we have to divide by the molar mass of water, which we already said was 18.02 grams per 1 mole of water. So we just converted from grams to moles. So now we still can't convert directly to oxygen atoms because we're talking about H2O. However, we do know H2O is a covalent compound, so it is a molecule. So we can use Avogadro's number to convert to molecules of H2O. So we know for every 1 mole of water, there's Avogadro's number of molecules. And when you do all that, we get 3.341 times 10 to the 24th molecules of H2O. So we still have to do one more step. We have to convert to the number of oxygen atoms. So now all you have to do is look in 1 molecule of H2O, how many oxygen atoms are there? So if you look at H2O, there is just 1 oxygen atom. Remember, you could read it as H2O1. So for every 1 molecule of H2O, there is 1 atom of oxygen. And here the molecules of water cancel. So that means, as our final answer, since we're just multiplying by 1, our final answer is 3.341 times 10 to the 24th atoms of oxygen. So sometimes if you're referring to a molecule, sometimes it'll ask for a specific atom within that molecule, and you just have to look and see, as your final step, how many atoms of that specific one are in that molecule. So the setup would be the same for all these others, and the last step, so for N2O, that last step would be the same. So here there's 1 atom of oxygen for every 1 molecule of N2O. Whereas these, in C3H6O2, so that last conversion, there would be 2 atoms of oxygen for every 1 molecule of C3H6O2. And same thing with CO2, that last step, you would put 2 atoms of oxygen. It would look like this, so 2 atoms of oxygen for every 1 mole, for every 1 molecule of CO2. So literally all you have to do for that last step is look at the chemical formula of that molecule. Okay, so one thing I want to stress with all these is that not every problem is going to be exactly the same. So you have to think about each problem and not necessarily memorize an equation. These are all conversions. So in order to problem solve, you have to first think about where you're going. What are you being asked for? So the way that I would do that, so it says decide on the final goal, is what you're being asked for. You always know the final units. I would always write those down at the end. And at the beginning, think about where you're starting from. So how do we get there? So always write down what's given to you so you know where to start. So you have where you start, where you're going, how do you get there? I would work backwards. You always know those units have to cancel, so be meticulous. Be careful that you label every unit, as every unit will have to cancel until you get to your final goal. And then always think about if your answer makes sense. Check it. If an atom weighs 15 kilograms, that calculation is probably incorrect. Okay, so the process, I want to stress that the process is most important. See you next time.